Okay, the people I don't see are Denford and Andrew. There's Andrew. Okay, we're going to talk about momentum. We ended last class period just beginning talking about momentum. Does anyone remember what the equation for momentum was? Or the symbol for that matter? P is the symbol. And what's it equal to?
Mass times velocity.
Mass times velocity. I put arrows over it. What do the arrows mean? It has direction. It's a vector. Excellent. So we're going to talk about momentum some today. I ended last class period with the little picture of the guy dropping the ball. And at the bottom we had Newton's second law that said net force is mass times acceleration. And then I said, but acceleration is just the change in velocity divided by the change in time. And so making that, you get what is actually, that wasn't supposed to happen, the more accurate form of Newton's second law, that the net force multiplied by the change in time is equal to the change in momentum. So that means if the net force acting on something is zero, the momentum will not change. Actually goes correctly back to Newton's second law the way we talked about it before. You'll have constant motion unless there's a net force acting on it. Was the first law. The second law said that that net force would cause an acceleration according to this relation. So it's no surprise, but it's useful to us because in a lot of situations, momentum will remain constant. For instance, let's suppose that I am in a car with no friction whatsoever. Of course, that means I couldn't speed up or slow down, but let's ignore that. My car is moving. As long as I'm on a flat surface, my momentum is going to be the same. Now let's suppose that my car is moving and there's another car that also has no friction that's coming toward me. When I hit that car, is that car going to put a force on me? Yes. So will my momentum change? Yes, because there is a net force acting for some time delta t will change the momentum. But if we consider both cars together, then the force between the cars is going to add up to zero. And so if I take my system as both cars, when the two cars collide, the net force acting on the two cars is zero. So that means the total momentum of the two cars is going to stay the same. So if we have two cars that hit each other, the momentum combined between the two won't change. It will shift from one to another, but the total will stay the same. This is used all the time in things like traffic collisions. When you have a traffic collision, you got this car driving down the road and it hits that car. One of the first things the police officers do after, of course, doing the safety things, is to get out their little wheel and measure the lengths of skid marks and carefully document where the skid marks start, where they end, and so on, because with those skid marks, they can calculate, okay, this vehicle skidded for this distance before the collision. And when it's skidding, you know you have a force that's changing the velocity. What do we call the force when it's skidding? Okay, it's one of the two kinds of friction that we focus on. Kinetic friction. It's the force of kinetic friction because they were sliding between the two surfaces. And so if you know the mass of the car, then you can calculate what the force of gravity downward of the car was. Assuming the only vertical forces are the mass times gravity, force of gravity downward, and the force normal upward, then you can know what the force normal is. Rubber and asphalt, we just have to look up in a table what the coefficient of kinetic friction is between getting my words confused. I'm going to start by writing the equation here. Force of kinetic friction, so Kf for kinetic friction, is equal to the coefficient of kinetic friction times force normal. So to find the force normal, take a free body diagram of the car, vertical forces, force of gravity down, force normal up. Sum of the forces in the vertical direction, I define y as the vertical direction, is equal to mass times acceleration in the y direction, which is 0, as long as the car is on a flat surface. It's not accelerating upward or downward. Its vertical velocity staying constant at 0. And so that's going to be force normal minus force of gravity equals 0. So force normal equals force of gravity. So we know that value. The coefficient of kinetic friction, that's where I stopped. That is something that you look up in a table. You have rubber on asphalt, which I think is spelled something like that. May not have the U. I did not look it up. And so you just look at the coefficient of kinetic friction for rubber on asphalt, and then you can calculate how much force friction was doing on that car. Why would we want to know that force? Because it was doing work. It was slowing it down. You can either use work energy and say the kinetic energy initial, well, better do it the other way. Kinetic energy final minus kinetic energy initial is by definition the change in kinetic energy. But from our work energy relation, that was equal to work net. And work net is going to be the force horizontal, which is the force of kinetic friction, times the distance of the skid. So I can relate what the kinetic energy of the car was when it hit the brakes to the kinetic energy of the car when it hit the next car. Now that's not enough to know how fast they were going, because I need to know how fast they're going at the collision if I'm going to find out how fast they're going before they hit the brakes. So we do the same thing for the other car, and then we say, and during the collision, remember the equation up at the top here is that the change in momentum is the net force multiplied by the change in time. During the collision, you still do have the kinetic friction going on, right? The cars still are going to have their tires sliding a little. But that's a small force compared to the force of the collision. Right? The force between the two cars hitting is much greater than the force that you were getting from the tires. Hence, you stop a lot quicker when you hit something than when you just are on the brakes. We try not to do that by example. So, because it's a much smaller force, the force of skidding compared than the force of the collision, and the time of the collision is exceedingly small, right? The collision doesn't last 5 seconds. The time between when they strike and when they either bounce off each other or stick together is virtually 0 time. And so they say, okay, so that force net multiplied by the change in time just during the collision part is approximately 0. So they say the momentum that the two cars had just before the collision is the same as the combined momentum after the collision. And then you go for, okay, now we have the last skids at the end of the collision when the cars stop, they're at rest. So the kinetic energy final then is going to be 0, and they can calculate what the kinetic energy of each car was by the skids after they hit to determine what the momentum was right after the collision. Using conservation of momentum, because there's no change in, the net force times the time during the collision is approximately 0, they then can calculate what the momentum of each individual car was just before the collision. And then these equations allow them to go back and say, aha, so this car was doing 85 and this one was doing 30, and it was in a 25 mile an hour zone. The one that was going 30, we'll give him a, you're okay, you're only 5 over. The one that was doing 80, he's going to get a serious ticket for speeding, causing this dangerous collision. So this physics here, talking about collisions and momentum, now we're going to learn more about collisions in lab today. It has a very practical application in trying to determine what happened when cars collide. Now there's a word here that I very rarely use, impulse. Not because I lack an impulse control, it's a true statement, but not the reason I don't use it. The reason I don't use it is because impulse is a word used to describe this right here. The net force multiplied by the change in time that net force is acting. But there's an equal sign. What is that impulse equal to? you look at the right side of the equal sign, what's it equal to? Going one past. Change in momentum. So the fact is, impulse is just equal to change in momentum. So this and this are equal to each other. I don't like to have two words for the same thing. And to me, change in momentum, okay, technically change in momentum is 3 words. But change in momentum is much clearer than impulse. And they equal each other. The technical differentiation on when one should be used and when the other should be used is if you're actually multiplying the net force, multiplied by the time that it acts, then that's impulse. If you're measuring the mass times velocity and the change therein, that's change in momentum. But the two are always equal. Why are they equal? They're equal because Newton's second law says they're equal. And we have tested Newton's second law in lab. And so hopefully you have a little more confidence in it than you would have otherwise. Now, examples of momentum. I don't have a bowling ball out here anymore, but I do have a tennis ball. And I can take this tennis ball and I can take this ping pong ball. If I throw both balls at the same speed, now keep in mind, tennis balls are heavier than ping pong balls. If I throw them at the same speed, how will their momenta compare? Momentum is what times what? Mass times velocity. So they have the same speed, the same velocity, so I'll throw them in the same direction. But different masses, how will the momenta compare? Momenta is, by the way, the plural for momentum. They'll be different. Which will have the higher momentum? The heavier one, the tennis ball. Now, throwing these won't really do anything because you can't see momentum. But you can see how air resistance is going to affect them. Which one of these two balls will have the bigger air resistance? The tennis ball, because two things. It's bigger and it has this nice fuzzy exterior. So I throw them, the tennis ball has a bigger air resistance. So the force of air resistance is going to be bigger. But let's actually see how they compare when I throw them. Like, does one of them fall first or fall short? So I've actually never done this before, which means I'm not sure how to throw two balls at once, but I think we can do it here. Okay, so which one went farther? The tennis ball. If, assuming that I threw it correctly, they both left at the same speed, what would make the tennis ball go a farther distance? It had more mass. Because it had more mass, it had more momentum. And so looking at that equation, well, it's not there anymore, but the impulse change momentum equation, if it has more mass, it's going to take either the same force in a larger time or a larger force in the same time to cause the same change in momentum. The resistance force basically was proportional to the cross-sectional area of these. So this one, is maybe 4 times the resistance force. But if its mass is more than 4 times greater, then it's still going to go farther. It's going to be slowed less. This actually plays into, did I tell you guys about racing and skiing and air resistance? Or is that a different class? Okay, when you're racing on skis, if I were to race any one of you, I actually would have a pretty good advantage because I'm really heavy. And since I'm really heavy, the air resistance is going to be a smaller percentage of the force of gravity pulling me down the hill. So the net force acting on me is going to be actually bigger down the hill because I'm more massive. Of course, and if I could still get into a tuck, these days I don't think I could, our air resistances would become very similar if I was in a tuck. But being much heavier, I have a much bigger downward force. With the same upward force, I would accelerate quicker. That's the key to me in ski racing. All the way until you get to, doing slalom. Yeah, slalom being heavy is not good. For pretty much the same reason. So this picture here is comparing the momentum for a light ball and a heavy ball with different speeds. So if you look at this graphic, you have a bowling ball with a mass of 7 kilograms. It's a pretty heavy ball. 7 kilograms would weigh somewhere around 15 pounds. 15 and a half or so. And it's going at 2 meters per second. So it's momentum. We calculate momentum by taking A times B, mass times velocity. So I take my 7 kilogram mass, multiply by my 2 meters per second velocity, and I have a total momentum of 14 kilogram meters per second. So our units for momentum, kilogram meters per second. Now we have this tennis ball that's about 0.07 kilograms, 1/100th the mass. And it's traveling at 200 meters per second, 100 times the speed. That gives it the same momentum. So the bowling ball and the tennis ball, I think we'd all agree, a bowling ball is rather hard to stop. Now 2 meters per second is not going very quick, but it's rather hard to stop. Tennis ball is easy to stop, but if the tennis ball is coming at you 200 meters per second, well, that's super quick. And that's going to be really hard to stop as well. And in fact, they would, if the time of impact on you, like if you're sitting here, going to hit me on the chest, if the time of impact was the same for both of those, and they just stopped when they hit you, there's no bouncing, they would have the same amount of pain, provided it's spread over the same area. That's another important thing. If it's over a smaller area, the smaller ball having a smaller area, it's going to be doing more damage to that small area. The bigger one is spreading it out, so it's less overall. That's actually one of the goals. You wear a bulletproof vest. That bulletproof vest, instead of having the bullet just hit here, essentially the bullet hits this whole area. Still hurts, it still pushes hard on your chest, but you have that whole area that's absorbing instead of that small area. That's why people wear those things. Because you have to stop the momentum of the bullet in both cases. Okay, and this has nothing new on it whatsoever. A practical example of dropping a ball that actually bounces up to the same height you dropped it. Do I have any balls that do that? No, I don't. Do balls exist that do that? No, they don't. We talk about the coefficient of restitution, and that coefficient of restitution tells you about what percentage of the energy will be returned when it bounces. And for something like a steel ball, that coefficient of restitution can be like 0.97, which means 97% of the energy is returned. For our purposes, we'll say it returned all of the energy if it returns 97%. But practically, it didn't return all of it. So saying here that the ball comes down, hits the ground, and bounces back, and has the same upward velocity, well, not really possible, but that's saying it returned all the energy. Because just before it hit the ground, it had kinetic energy of, what's the equation for kinetic energy? 1/2 mv squared. Now, if we look at that in terms of momentum, I can write that in terms of momentum. Kinetic energy equals 1/2 mv squared. But since momentum is equal to mass times velocity, then velocity is equal to momentum divided by mass. And so if I put that in here, I get kinetic energy equals 1/2 mass times momentum divided by mass quantity squared. Just expanding that. Well, what's m divided by m squared? Just 1 over m. So this is equal to momentum squared over 2m. So you can also write kinetic energy as momentum squared divided by 2m. And so if I have a ball that has momentum p, its kinetic energy is p squared over 2m. If I use the same ball, if the magnitude of the momentum is the same, its kinetic energy is the same. So this problem here with the ball bouncing and hitting the ground with p downward and ending up with p upward being the same value, that's saying it has the same energy returned. Does the ball have a change in momentum when it bounces? if the final momentum has the same magnitude as the initial momentum, does its momentum change? It's a yay or nay question. Yes, it does. That's the correct answer. Why is that correct? Okay, that was all I heard was mumble.
It changes direction.
It changes direction. Right? So because the direction changed, its momentum changed. And so the change in momentum is always final minus initial. The initial one had the velocity going down, so I'll put the minus v right there. mv minus m times initially minus v. That turns out to be 2mv as shown right up above. So when a ball bounces, it changes momentum. If it changes momentum, that means there had to be a net force, and we could calculate the impulse by, well, at this level, we look at graphs to do that. Now a clicker question for you that has to do with momentum. Two football players collide during a tackle. Which player exerts the larger force than the other player? This would apparently be the Houston Oilers and, let's say, the New York Jets. As a follow-up tricky question, what do the Houston Oilers and New York Jets have in common? The Houston Oilers were originally, well, you don't know, do you? They were originally the Houston Oilers and they became the Tennessee Titans, right? And the New York Jets, what did they start out as? The New York Titans. Right? So they're both the Titans. Kind of cool, right? Just like you guys know what the Kansas City Chiefs were originally. I wasn't alive then. I don't want you to think that I was alive. Do you know where they started? No. They were the Dallas Texans. And so both Texans and Titans has been reused, which I find interesting. Okay, we have everybody's answer now, so I can move on. Okay. The two football players collide during a tackle. Which player exerts the larger force than the other player? This is how many correct answers we have. So let's discuss this. Right? We bring up new ideas and you sometimes forget the originals. You figure out what you did wrong? Can you tell us what you did wrong?
They'll exert the same force on each other because they're acting on each other.
Yes. Newton's third law says if I hit Colby, he hits me with exactly the same force in the opposite direction. This question is one of the ones that's really hard for us to internalize. We tend to think things like, a VW bug hits a semi-truck. Which one is going to get damaged the most? The bug, right? And so we tend to think that the force on the bug was much bigger than the force on the semi, but it's not true. Newton's third law says it's the same. So why does the bug get so much damage and the semi not much? Because the bug is built really strong. That was a lie. The bug is not built very strong, whereas the semi is. And so the same force caused major damage to the VW bug, and the semi is like, oh no, I'm going to have to buff that out. You know. Same thing here. You have the two football players. You've got, in this case, that's got to be a safety because only 75 kilograms. Y'all know how much 75 kilograms is? 165 pounds. The number of players in the NFL that are 165 pounds, you can count on one hand. And they tend to be wide receivers. Because that's Well, you're not built that strong when you're 175 pounds compared to somebody who, 100 kilograms, how heavy is that? 220. Somebody with a mass of 100 kilograms, that's 220. That's just a nice, beefy sized dude. Way less than me, but, you know, at my best, I would be 100 kilograms. So you have these two guys, you have the collision, and the one with 100 kilograms has more momentum. He's going faster, and he's got more mass. He has more momentum. He's going to deliver a bigger hit, but they're both going to have the same force. It's just the other guy's going to receive more. You know, that is, when he gets hit, what is the direction of what is the total momentum between those two players? It's going to be 500 minus 300 because they're opposite directions, so 200. So you have 200 kilogram meters per second is your momentum. If they hit each other and they just stick together, and if you're getting nothing from the ground, it's just, you know, momentum's conserved, in the end you're going to have 175 kilograms. You have a total of 200 kilogram meters per second still to your right because momentum is conserved. So they're going to be going 200 divided by 175, that's 200 divided by 3/4, 800 divided by 3, well, 800 divided by 3 times what it comes up to. What is that? Actually, it's not 3/4, it's 200 divided by 7/4. So 800 divided by 7. That's what their speed is going to be. 800 divided by 700. So they're going to be going this direction after the collision. Who had the bigger acceleration? This guy goes from 5 to, let's say it's 1.2, just to put a number on. 5 to 1.2. This one goes from minus 4 to 1.2. He changed 5 point something. He changed 3 point something meters per second in the same amount of time. So the little guy had the bigger acceleration. But they have the same force. Net force is equal to mass times acceleration. So acceleration is net force divided by mass. Littler mass, bigger acceleration. But if you're, like measuring how comfortable it is, that bigger acceleration is going to be less comfortable, generally speaking. So this guy's probably going to feel it worse even though they had the same force acting on him. And in terms of kinetic energy, if you calculate the kinetic energy, this guy goes from p squared over 2m, so 500 squared. That's 2.5 times 10 to the, I don't know. Divided by 2 times his mass, so divided by 200. I'm not going to do the calculations. I don't have my calculator out and I don't want to do them. But in terms of kinetic energy, the change in kinetic energy for this guy is bigger because basically he stops and then starts going the other direction than that guy's. Okay, the key why I had this question here was just one thing though. I want to make sure we can separate the size and momentum from the force and not have that confusion. And as we saw, everybody had that confusion, but then we figured it out. They exert equal forces. So, there was my answer. Why do I give the question? Because it's something we have a hard time grasping. So Newton's third law still holds. You still have the same force, but the defensive back responds with a greater response to the same force. Okay, so now we're actually going to do a problem here. What is the initial momentum of each player? Well, it's calculated right here. How did that calculation occur? And this one here was P2 initial mass 2 V2 initial equals 75 kilograms times minus 4 meters per second. What does the minus 4 signify? It's going the negative direction, right? It's important that we remember what those directions mean. And so we have how we calculate those two values. Now, a different but related problem. This one has a very practical application, at least for me. Two skaters of different masses prepare to push off against one another. Which one will gain the larger velocity? Okay. 081. 8 people said the less massive one will have more. Well, let's go and look at the calculations here. We have 2 people. Person 1 that for fun we'll call Richard. And Richard has a mass of, back then, 100 kilograms. And person 2 that we'll call Nalco. I know, strangely specific names. Has a mass of about 50 kilograms. So these numbers are true to life. So Richard and Nalco are sitting here and they push off of each other. So let us say that they push with a force of 100 newtons and for a time of 2 seconds. What's going to happen if we have a force of 100 newtons between the two for a time of 2 seconds? First thing I need to ask. I said that force is 100 newtons. What is the net horizontal force acting on Richard? 100 newtons in what direction?
Right. Or no, to the left.
On Richard, it's going to be acting to the left. Correct. So Richard has a net force and I'll put minus 100 newtons because of the direction. What about the net force for Nalco? Whoops, not 1,000, 100. Yes, you're right. I just got carried away with my zeros. Okay, so each one has a net force of 100 newtons. Sometimes we say, well, shouldn't it be split 50-50, so it's 50 on each? No, back to Newton's third law. Richard pushes with 100 newtons on Nalco. Nalco pushes back with 100 newtons on Richard. So now we look at what's going to happen to Richard. Richard should have change in momentum is equal to force net multiplied by the change in time. And so that's going to be change in momentum. That's mass of Richard times the speed of Richard final minus the mass of Richard times the speed of Richard initial. Now, of course, we started from rest. So the initial speeds were 0, and I can immediately calculate the final speed for Richard. How fast would Richard be traveling? Not only did I choose these numbers to be accurate, but they're also easy. Should be minus 2 meters per second. Now, what about the average acceleration for Richard? What's the equation for average acceleration? You don't have to have the equations memorized, but the ideas are important. What is acceleration? Yeah. It's the rate at which velocity is changing divided by the time, well, per time. So that would be the final minus 2 meters per second minus the initial over the 2 seconds. And so the acceleration of Richard was minus 1 meter per second squared, and his final velocity was minus 2 meters per second. Now, if we do the same calculations for Nalco, you just change the r's to n's. So all the equations come out the same, I just have to change the numbers. So for Nalco, speed for Nalco final should be 100 newtons times 2 seconds divided by her mass of 50 kilograms. That's 4 meters per second. So she ends up going at twice the speed, opposite direction, and her acceleration is 2 meters per second squared, twice the acceleration. So the way I had this planned out, we were up here at Riverfront Park in Spokane. I'm going to show her this physics thing. And so, you ready? Yeah. Okay, here we go. Push. And what do you suppose happened? She fell. She fell. She fell. She cried. She was very angry at me. Oh, what? It's just physics. This is physics demonstrations. You know. But yeah, that doesn't work very well. To make matters worse, we're using rented ice skates. I take off my ice skate, and one of my boots is filled with blood. I'm like, ah, crap. I look around. No, not my blood. Somebody else's blood.
Ew.
Yeah.
Ew.
I would have been much better if it had been my blood. That was a great date. I tell you what, great date. So people have told me since then that probably physics demonstrations aren't the best thing to do on a date. How was I to know? Okay, going to some practical applications besides a physicist going on a date and failing. Shooting a gun. How many people here have fired a gun? Okay, that's about half. When you fire a gun, everybody knows there's a recoil. The gun goes back. Why does the gun come back? Why do they make guns so they don't do that? Because they can't. Why does the gun come back? Yeah, you have a gun. In the gun you have a bullet, and then you have an explosive that is going to, when you hit it, it's going to rapidly expand and push everything around it. So inside of the firing chamber, you have something that is stopping things here, and you have a bullet, and you have stuff that's pushing in all directions. Well, the bullet moves easily. And so the bullet goes whistling out here. The bullet has a low mass. You have a high force instead of 100 newtons like I was doing. It's probably a bigger force. Well, I don't know. I actually don't know. But you have a very low mass, a reasonably large force, a real big acceleration that pushes that bullet down the barrel. But you also have the gas pushing this direction. And so the gun responds just like the bullet, except for the gun is much more massive than the bullet. Because the gun is much more massive, the acceleration of the gun is much smaller. But momentum between the gun and bullet is conserved during the firing. Now, I don't know if you've seen the funny pictures on Facebook, but you have things like a person holding the shotgun in front of their face like this. What's going to happen when you pull the trigger? Yeah, because it's going to come back. Normally, you want, if you're shooting a rifle, you want that barrel against your shoulder, so your shoulder is part of the mass it's trying to move. And so it doesn't build up much speed because it's also pushing your shoulder. It is like having a hammer on your shoulder that you go, but it never got any speed up. If you start with it like an inch away from your shoulder, it comes wailing into your shoulder because it builds up that speed during the firing and then it hits you. Well, if you do it in front of your face, it's going to come hit your nose, and it's very funny to think about what might happen, except for if it were to really happen, then we'd be very sad. I would at least. I have a tender heart. So the gun is going to recoil because of conservation of momentum. You gave momentum to the bullet in one direction, the gun had to conserve and have momentum in the other direction until some other force, like your shoulder or your nose, slows down the gun. So that's a nice practical example of this whole conservation of momentum thing. Here's another one. This is an actual publication from July 17, 1969 in the New York Times. I will actually read this. I know you all can read. It's one of your skills. But I'll read it just so we all go through it. On January 13, 1920, Topics of the Times, an editorial page feature of the New York Times, dismissed the notion that a rocket could function in a vacuum and commented on the ideas of Robert H. Goddard, the rocket pioneer, as follows, quote, that Professor Goddard, with his, quote, chair, end quote, in Clark College of the Smithsonian Institution, does not know the relation of action to reaction, and of the need to have something better than a vacuum against which to react. To say that would be absurd. Of course, he only seems to lack the knowledge ladled out daily in high schools. Further investigation and experimentation have confirmed the findings of Isaac Newton in the 17th century, and it is now definitely established that a rocket can function in a vacuum as well as in the atmosphere. The Times regrets the error. It's kind of funny, right? But if you think about this, we should be able to decipher what the editor was thinking when he wrote the original editorial. He talks about the relation between action and reaction. What do we normally call that relation? For every action, there's equal and opposite reaction. Newton's third law. That's Newton's third law. And what this editorial writer, the editor, was thinking was that a rocket works by pushing off of something. Now, if I'm on the ground, I can push on the ground, and what's the ground going to do to me? Push back. So I push, and it pushed me back, and it made me go up into the air. So the editor was like, that's how things go. Now, if you go into the vacuum of space, there is nothing to push off of. And so the editor is saying that's kind of like if I am, suspended in the air, and I sit here and try to push with my legs, I'm just going to look silly, but not move anywhere. And you say that's what's going to happen with the rocket. That's clearly not what happened, right? The rockets do propel themselves out in the vacuum of space. So what was he missing? What he was missing was what really goes on with rocketry. With a rocket, you have fuel in that rocket, and that fuel burns. Burns means that you have a redox reaction, a chemical reaction, that converts chemical energy into kinetic energy. So you have these little molecules that were initially just bound together that break apart and start flying fast because of the energy released. Now with that rocket, how many people have seen October Skies? Only 2. It's a great movie, right? And they focus so much on the nozzle. The nozzle is super important because you have those particles moving. You want to direct all those particles one way, one direction. But no laying music involved. So you have all those particles going one direction according to Newton's third law, sure. Newton's second law, I don't care which one you look at. You start with everything at rest, and then you end up with some particles going in one direction, so they have a momentum in that direction. What does the remaining part have to do? It has to go the other. It doesn't rely on anything outside of the rocket. It's just the burning the fuel and making sure that the burnt fuel goes one direction so the rocket goes the other. So that's how rockets work. Now, there are other ways of trying to propel rockets besides burning things. things like using electricity and having little charged particles that you repel because of electric charge. But it's still going to have to do the same thing. You have to have these little charged particles that you repel, and in response, the rocket goes forward. So, in all cases of rocketry, essentially, you're throwing something out of the rocket to make it go the other direction. Now, this brings us to a very classical problem. I don't have a clicker question for this, so I just describe it. Here is a frozen lake in Minnesota. It's supposed to be very flat. Don't mind the fact that it's not. And you are sitting here, stuck in the middle of the lake. You have nothing with you but the clothes you're wearing. And this is really perfect ice, so it has zero coefficient of friction. There's nothing you can do. You can't dig in. You can't do anything like that. How can you get yourself to the side of the lake?
Swing your,
Do what?
swing your arms.
If I swing my arms, and I just go like this, okay,
No, roll.
roll. Then let me start with something here that you said that actually, if I start with my arms like this and I swing them like this, while I'm doing this, my body will move. But when I get up here and stop, it stops again. And to get my arms down here, my body will move back. And so in the end, that doesn't work. Rolling, if there's no friction, I'm just going to stay in place and tire myself out. There is a way, though, to get to the side. It has to do with what I started with. Nothing but you and the clothes you're wearing. Okay, well, let's be smart. Let's just take off our shoes, okay? Take off your shoe and find which... I'm going to throw my shoe. What direction do I want to throw it? Okay, opposite where you want to go. Now, some of us might say, oh, I'm going to throw it like a 45-degree arc. No. Because then you're going to be partially pushing down on the ice will be pushing up on you and taking away some of that. You want to throw it horizontally, the opposite direction you want to go. So you find the closest shore, turn and face the other way, and throw as hard as you can horizontally. Your shoe and you start with zero momentum. You threw your shoe, it now has momentum that way. You must have momentum this way. The harder you throw your shoe, the faster you'll go. If there's no friction, you're just going to keep sliding until you get to the edge of the lake, right? And if there was friction, well, there'd be other ways of getting there. But it's, okay, that's an example we use here on Earth that's kind of contrived because there's no lake that's perfectly no friction. But in space, it's contrived because none of us are going into space to do this. But if you're out there and you're on a spacewalk, let's say that you are, Sandra Bullock. You're out here and something devastating happens and you're disconnected from everything and you need to get over there. The only way to do it is going to be to throw something that way, in exactly the right direction. Now, you guys have seen Gravity, right? Horrible, terribly. There's no word besides horrible to describe that movie. Except for low budget, because how many actors did they really have? Yeah. For most of the movie, it was, the first core of the movie, there were 2. There were like 5 in the first scene. Then you have 2, and then finally you just have 1 for the rest. Had to be real cheap to make. Except for special effects stuff. And the logistics of, I'm just going to aim myself and eventually hit this satellite. Yeah. Think about the chances of you being in a cornfield here and saying, I'm going to walk this direction, eventually I'll hit Omaha. You're probably going to miss, right? Yeah. Now instead, magnify the distances by 1,000 and something much smaller than Omaha. Yeah. Anyway, it was just a horror bad movie. Last thing for today, we'll pick it up in lab today, elastic and inelastic collisions. Elastic collisions are collisions where the kinetic energy before the collision is the same as the kinetic energy after the collision. Inelastic collisions, inelastic means that you had some deformation that absorbed energy. So an inelastic collision, you're going to have your kinetic energy after the collision is smaller because some energy was absorbed. It went from being kinetic energy into something else. Like what we're going to have is Velcro. Velcro goes like this, catches and holds, and it absorbs that kinetic energy. You can have other things like you throw a rock into mud. The mud deforms around the rock and absorbs the kinetic energy. So an elastic collision returns kinetic energy, and inelastic absorbs some of the kinetic energy. And that's what we'll pick up in lab today.